Hello, everybody. Thank you for joining us today. My name is Ronaldo Pinto. I'm the Technical Sales Director for AFT. My email is ronaldopinto@aft.com. And today I'll be hosting today's webinar that we'll be talking about pulsation control, fundamentals, and problem solving. This webinar is being recorded, so if you're not able to finish it, you'll receive an email with the link to review the recording webinar. So the agenda today will have an introduction to pipe vibration, an introduction to vibration and piping system. Then we'll be talking about solving a field problem, vibration problem, and then we'll have a section of question and answer. Probably there will be a lot of questions because there's many attendees. If I can't answer all the questions, you'll receive an email with the answer to all the questions formulated in the webinar. So let's start. One source of pipe vibration are reciprocating pumps. As you can see from the animation, the flow is not supplied continuously. The piston fills the chamber with liquid from the inlet and injects it in the outlet. This creates a flow, a pulsation in the pressure, and consequently, the vibration observed in the field. The same thing happens for rotary pumps. In this case, different chambers are filled from the inlet and injected in the outlet, creating the fluctuation of the flow, creating the fluctuation of the pressure, and consequently the vibration observed due to this equipment. Now, depending on the design, the vibration is less severe or not. In this case, we have a duplex pump, single acting. The blue line represents the fluctuation of the flow of one piston, and the red line represents the fluctuation of the flow on the other piston. The combination of both shows the fluctuation of the flow observed on the graph. Now, if we have another design, a duplex pump, double acting, we could see the fluctuation of the flow in the dotted blue line. That is less severe than the duplex pump. If we continue to other designs, we get up to quintuplex pump, where the action of 5 pistons creates a fluctuation of the flow less severe than the duplex pump double acting and the duplex pump single acting. So let's watch a video of vibration caused by reciprocating pumps. Here we see the pulsation causes a vibration of the pole, and it can even cause a vibration of the structure. Here, so pressure pulsation is something we want to predict, because pressure pulsation can lead to cavitation, fatigue, pipe failures, reduced system efficiency, and reduced capacity. One of the key elements to solve a vibration problem is to determine whether the source of high vibration displacements is due to acoustical, mechanical, or mechanical resonance. And this is the approach that we're going to show in the webinar. Why is this? Because depending on the source of the vibration, the type of solution varies. If a mechanical solution is applied to an acoustical problem, or an acoustical solution is applied to a mechanical problem, it is unlikely the problem will be solved. So let's talk about vibration in piping systems. Pressure pulsation propagates through the piping system at about the speed of sound. Speed of sound depends on fluid properties, bulk modulus, pipe, material, diameter, and thickness. Pressure flow pulsation reflect at geometrical discontinuities. Wave reflection and wave interaction results in system acoustical natural frequencies. System will show an acoustical response to an acoustical excitation. Presence of acoustical natural frequencies may result in acoustical resonance. The phenomenon takes place when the return of a reflective pressure wave generated by a periodic excitation coincides with the generation of the next pressure pulse. The amplitude of the vibration response can be amplified 2.5 times or higher at or near a component natural frequency, resonant frequency. The stronger the exciting force and or the closer this exciting force are to natural frequencies, the greater the vibration amplitude will be. The importance of liquid acoustical analysis is reflected in API 674 standard. AFT Impulse PFA module pulsation frequency analysis uses a digital simulation technique to model the acoustical behavior of the piping network. Acoustical simulation can be employed to calculate the acoustical behavior of the liquid in the piping system. With acoustical simulation, the system dynamic can be understood in advance so that problems caused by pressure pulsation can be minimized or avoided. How? For a physical system, a physical hammer is used to introduce energy in the system. Sensors pick up the excited frequency. A special tip on the hammer can be applied to excite a specific frequency range. What about acoustical models? You need to use a software that can model the propagation of the acoustical waves. In this case, you use a numerical hammer. You use a fast Fourier transform to convert the time results into frequency domain. You add a filter to the numerical hammer to excite the specific frequency ranges. So we have a system here and we want to study the acoustical natural frequencies. So we apply a hammer, a numerical hammer, at this point where the pump would be. The numerical hammer is applied by a sudden change in the volumetric flow. We applied the low pass filter to apply it to the low frequencies. As I said, we apply it at the pump. And then we take it to the frequency domain by the fast Fourier transformer. That's what the program PFA does. Pressure pulsation is a tonal form of excitation whereby dynamic pressure fluctuations are generated in the process fluid at discrete frequencies. Pressure pulsation results in dynamic forces being applied at bend, reducers, and changes of section. And these forces can be very high, shaking the whole system, and it can be dangerous for the system because it can cause fatigue in the system. For pulsation to result in significant levels of vibration, The dynamic force must couple to the mechanical response of the pipe network. So we're going to see a graph. In the frequency domain, to experience high levels of vibration, the frequency of the source of excitation must correlate with the acoustical natural frequency, resulting in high levels of pulsation. This in turn must correlate with the mechanical natural frequency to cause high level of vibration, as shown in figure at 40 hertz. So what do we have here? We have the 5 graph. The acoustical excitation, the acoustical natural frequency will be calculated in the acoustical simulation. The pulsation response results as the response of the system, the mechanical natural frequencies, and the resultant vibration observed in the field. So let's talk about 40 hertz. What happens at 40 hertz? Excitation coincides with acoustical natural frequencies. So we see that the excitation here has 40 hertz that also is present in the acoustical natural response of the system. This has the result of high pulsation. So we have high pulsation, and also pulsation coincides with mechanical natural frequencies. So we have a mechanical natural frequencies of the system of 40 hertz. Result, high displacement. Let's see another case. 60 hertz. If the mechanical natural frequency does not correlate with the pulsation, as shown in 60 hertz, then the amplitude of this force vibration will be significantly lower than the resonant response. So let's see 60 hertz. What happened in 60 hertz? Excitation coincides with the acoustical natural frequency. Consequently, we have high pulsation. But the frequency of the pulsation does not coincide with the mechanical natural frequency. Consequently, we have low displacement. Let's see another case. If the acoustical natural frequency does not correlate with the excitation, then there will be little pulsation and therefore lower vibration level, shown in figure at 20 hertz. So for 20 hertz, excitation does not coincide with acoustical natural frequency. So we don't have an acoustical response for 20 hertz. Results, low pulsation. Consequent result, low displacement. Conclusion. For most serious vibration problems, the frequency of the excitation, acoustical natural frequency, and mechanical natural frequency must correlate. However, high levels of non-resonant vibration can be experienced if there is a significant level of excitation present in the system. So let's see how we approach solving a field vibration problem. In this example, we have high vibration. We have a pump. And we experience a high vibration in pipe 12. So first step, we do field vibration measurements in the field. So we see that the predominant frequencies is 16 hertz, 33 hertz, 49 hertz, 66 hertz, 83 hertz, 99 hertz. Now, second step, determine if the vibration is result of acoustical resonance. For this, we do an acoustical model. And we're going to use AFT Impulse module PFA. From the acoustical vibration, we see that the most critical frequencies, or the highest frequencies, for 33 hertz and 93 hertz. For the rest, 16 hertz, it's present there. The frequency, acoustical natural frequency, 16 hertz, 49 hertz, and 65 and 83, but they're very low in response. Conclusion. Vibration peaks at 33 hertz and 99 hertz are most likely due to acoustical resonant conditions based on the high amplitudes. Vibration for peaks 16, 49, 16, 66, and 83 hertz are most likely due to mechanical resonant condition. However, each of these show evidence of acoustical resonance, but amplitudes are lower. Step 3. We calculate the mechanical natural frequencies. In this case, we use Caesar-2. We did a modal analysis. From the modal analysis, we see that mechanical natural frequency of 33, 34, 48, 84, and 98 are present and coincide with the ones measured in the field. Conclusion. High vibration peaks at 33 hertz and 99 hertz are both mechanical and acoustical. So this is probably the frequencies you want to address first to solve the problem. High vibration peaks at 49 and 83 hertz more probably are of mechanical nature. High vibration peaks at 16 and 66 hertz most probably are of acoustical nature, but acoustical amplitude are low for this, so this is uncertain. So what would you do to solve the problem? There are acoustical solutions and mechanical solutions. For acoustical solutions, you can change the operation of the input drivers to avoid exciting the resonant frequencies. Installation of orifice plates, increasing the diameter of the pipe, relocating closed valves, installation of additional volumes. For mechanical solution, you can do installation of additional support to reduce the flexibility of the pipe, relocating or improving quality of the supports. Sometimes, like U-bolts are not recommended to be used where you have vibration problems. Increasing the stiffness of the structure on which the system is mounted. So let's see in the example of PFA what we did before we move on. Here we have the problem and the model. And we want to apply the numerical hammer right here at this point and see the natural frequencies of T12 to see if they coincide with the natural frequency of the excitation observed in the field. So the first step would be to set up the pulsation, give it the characteristic of the PD pump. Here, we tell it where to apply the numerical hammer. In this case, would be in the pump. We input the characteristic of the pump, 5 heads, 250 RPM, And here we apply the filter. PFA will apply the filter automatically, but if you want to go below the filter and see, like here we have up to 140 hertz, you might want to only observe the frequencies below 100 hertz. So now we see the results. Now we have a new tab that's called frequency. So where the problem we're observing is in pipe 12, we can see the inlet because it's very short. So now we tell it to generate it. And here are the frequencies that are observed in the field. So we saw 33 hertz that we observe in the field. So 29 wouldn't be. 29. 33 hertz. This is what we're observing. We also observe. So we keep on, we try to see if the frequencies show up in the acoustical model that we are measuring in the field. Now, where do we compare it? We use API 674 to compare the levels to see if they're critical. So we use PFA to generate in a scenario to see if it complies with the code. Here, we would generate in the scenario for 107, if the pump operates at 135 RPM, and PFA would create the graph or the pulsation excitation to that speed. API 74 is petrochemical and natural gas industry reciprocating and displacement pumps. It has a allowable for peak-to-peak pulsation limits, which is this equation here. It's for international metric units, it would be 100 divided by the internal diameter by the frequency, the square root. So PFA would tell you whether or not you're compliant with the code at that if your pump operates at that frequency, at those RPM. So let's see how to generate that. We see this high level of vibration, the high response, and we would say, okay, let me see this one because this one would be critical for us. If I try to evaluate the excitation frequency, it would give me a message telling me that this frequency of 2.3 hertz has would be not excited by the pump speeds that are between 120 RPM and 280. So this is a frequency we don't have to worry about because it wouldn't be excited by the pump. So let's see this one here. and we want to check by API 74, the same message. So let's see this one here. This one here is already, it would be excited, and I created already the scenario for that. So the frequency of 13 hertz, 13.8 hertz would be excited if the pump RPM are 165.6. So now I would tell it to create a scenario to check that if the pump operates and if it's within the allowables. The scenario is already created. It would generate it automatically for you. So now in this scenario, the pump curve is generated here. Show graph. And it's applied to the system based on what you gave him. This is a quintuplex pump that we gave him the characteristic when we started the model. So now if we go to results, we have a new tab that is called Applied Standards. And based on this, it says API 74 errata positive displacement pump. All pipes were examined for maximum peak-to-peak pressure. All pipe and limits, so they comply. The peak-to-peak limit would be, the maximum pressure would be in pipe 31, and the peak-to-peak limit is station 21. The DP would be 0.18. The maximum allowed by the code DP would be 1.31. So all the system, if the pump operates at 132, would be according to allowable on the piping system, API 674. So there's some things that you have to consider when you model an acoustical model. Accuracy of prediction of acoustical natural frequency is relatively good. The error margin is small, 5%. Errors are controlled by limited parameters, geometry, speed of sound, drivers, RPM. So conclusion, acoustical solution based on acoustical models are more likely to be effective due to the precision of acoustical model. Now, in mechanical model assessment, accuracy of prediction of mechanical frequency is relatively low. The error margin is between 10 to 20%. And we know that when we do a mechanical model of a piping system, there's a lot of parameters to be that we can't control, like the modeling boundary conditions, modeling the rack structures, support clearance, support lift operations, support settling, support stiffness of clamps and restraints, friction, nonlinear supports, uncertainty of masses, difference between build and design. So in conclusion, mechanical solutions of mechanical model are less likely to be effective due to the imprecisions of the mechanical models. So let's finish another frequency according to API 674. Go to graph results. So this is another one we would like to examine to see if it operates and what frequency, what RPMs the pump would have to operate at. 25 hertz. Or let's examine one that we measure in the field. Let's look for 33 hertz. Here's 33 hertz. We want to evaluate. So now we would see that the pump speed would be 203 at the second harmonic and 135 third harmonic. So we want to create a scenario for both of them to see if it complies with API 674. So we would tell it, the program, to create a scenario to check these. Well, I'm going to discard this because we already examined this. So, and I'm only going to examine one. So this one I don't want to examine. I want to examine if the pump operates at 203. So it created a scenario for 203. So now the pump of the curve, 203 operating at 203 RPM, would change. This is a new curve. And we're ready to run it. It will take some time. So now it's checking all the system for 203 RPM. As I said, it takes some time. So you can see how easily you can check for different vibration excitation to check whether or not your pump can operate. And if it does operate at that range, what would be, how close it would be to not complying with the API 674. I'm going to end this because it would take too long to generate the results. So with this, I conclude the webinar, the introduction of a vibration problem. If you have any questions, please write it down. Well, there's no questions. I imagine that you'll receive an email with your questions later on. Thank you for listening. If you want to try PFA module and you're an Impulse user, just write it to sales@aft.com and we can activate a license for you. Thank you again for listening. Hope you see you in other webinars.